Hi students, welcome to Science Extension and Module 3, the Data, Evidence and Decisions. This is video number 17, and we're going to introduce this idea of the difference between correlation and causation. What you need to be able to do is to describe the difference between correlation and causation. So Bruce and Bruce suggest that the correlation coefficient measures the extent to which two variables are associated with one another. In science, we often want to know more than just a relationship between two variables. We actually want to know the extent to which changing the independent variable will affect the dependent variable. Sometimes we might even be able to work out a mathematical relationship between these two variables. So what we want to try and do now is to see if there are ways of turning that correlation coefficient, or turning something that we think has some relationship between two variables, into something that we can be a little bit more confident about exactly to what extent the independent variable is causing a change in the dependent variable. And to do that, we need to introduce another little term known as regression. Regression is the statistical technique that relates the dependent variable to one or more independent variables. The regression model shows whether changes observed in the dependent variable are associated with changes in one or more of these variables. So we can actually now statistically test the degree to which the dependent variable actually depends on the independent variable. Most of the time in science, there's not going to be a lot of difference between correlation and regression, and certainly nothing much in the statistical calculation. But there is going to be a little bit in the interpretation, and there's also going to be some other factors that we'll talk about in subsequent videos that you are going to need to apply to your data, as well as the calculations that you see in this video. According to McDonald, the main difference between correlation and regression is that in correlation you sample both measurement variables randomly from the population, while in regression you choose the values of the independent variable. And you'll know that that's what we often do in science. We decide what our values for the independent variable are. That could be as simple as, I'm going to vary the temperature and see what happens to the reaction rate of a particular chemical reaction. But I'm going to choose the values of 10 degrees, 20 degrees, 30 degrees, 40 degrees. That's what we mean when we talk about choosing the values of the independent variable. We're then going to measure our dependent variable, record those values, and see to what extent the dependent variables actually depend on those changes that we've made to the independent variable. Now, something that's important to keep in mind, and there's lots of things to keep in mind. In fact, you'll find a whole lot of data around graphs that look very, very similar, and you can talk about very strong correlation, but absolutely zero in the causation department. And we'll look at some of those in the next video as well. But even just reducing the range of values that you have, even when a relationship appears fairly strong, can reduce the value of your calculation statistic. So you can see some simulated data showing the effect of the range of x values on the R-squared calculation. For the exact same data, measuring y over a smaller range of x values yields a smaller R-squared. So that's one of the things to keep in mind as we talk through some of these issues relating to correlation, regression, and causation. The most critical thing to remember about correlation is the fact that you get a nice straight line, or you get data that fits very closely to a straight line. Maybe you get a value of 0.91 and you go, this is a brilliant value, I'm really happy with this value. Does not necessarily mean that your correlation implies causation. Depending on the data, the collection method, what we will call confounding variables, there could be a relationship between the two variables that we're looking at, or there might be a relationship without there being a cause and effect, or there might even be a third variable that's even more important to the two that we are looking at or measuring, and that third variable is the one that's really doing all the hard work in this case. So this needs to be reflected in our conclusions when we interpret the p-value and also the r-value that we calculate from our regression analysis. Here's the difference. When we invoke causation, what we're saying in effect is that as we change the x variable in a particular direction, there will be a consequent mathematically predictable change in the y variable. That is, you will know exactly what the y variable will be. And this is why we do things like interpolation or even extrapolation when we extend some of our graphs. We are saying there's a predictable relationship here, and it's so predictable that if I give you a value of x, you can calculate a value for y. And what we're effectively saying in this case is the change in x has caused the change in y. There's a direct relationship between x and y. Now, you'll know that if you're going to be doing a scientific investigation, you're going to want to be able to conclude this. You're going to want to be able to say, when I changed x in this direction, in this way, I observed a change in y, and that's what I was expecting, a relationship between these two variables. Now, as always, it takes good scientific design to ensure that the only variable that could be causing the change observed in the y variable are the changes in the x. And so you need to think about the use of things like controlled variables. Because if you don't control all your variables, then you are potentially going to introduce other things which may have affected those changes in the y variable. If we're seeking to establish cause and effect relationships in our research, it's critical that we not only see a correlation between the variables, but that we can also invoke causation. And one of the things that we might do to help us with this is to calculate a regression statistic. So I'm going to go back and I'm going to have a look at that kangaroo data again. This was the data that we looked at to try and work out whether or not there was a correlation between them. So one of the things that you'll notice when you look at the data analysis tools is that I have a tool called regression. Now, I should point out at this stage that you will also find further up here, just off the scale at the moment, one called correlation. So you can see covariance. There's one called correlation. So you can actually do a correlation test with this as well. And we might just have a quick look at that in this video. But you can see the kangaroo data. You can see the length versus width calculation that I looked at before. And what I've done is basically the same thing. I've done the calculation, this time based on a regression analysis. And I've picked where my y value is and my x value. And you can see one of the differences when we do this particular calculation is we are specifically looking at the x values and how they change in relation to the way that we've changed those x values. So we're specifically looking at the y values, and we're seeing what effect our change in the x values has made on those y values. You can see if I select the whole table, I can also include the labels in the table, and that's nice because that will come out in my data analysis. And you can also see there's a confidence interval. So the confidence interval is always a 95%. So we've continued to use our 0.05 alpha level. And I've again got an output range where I've put this into my spreadsheet. Now there's a few other things in here that you can have a look at as well, but I wouldn't go down this path too much unless you think it's going to be relevant for your own study. The one difference here is that you can actually see that this will calculate for me a value, a test statistic, and also a p-value. So this is my p-value. And so the nice thing about this regression statistic is this will also give you a p-value, which means you can then use it to accept or reject your null hypothesis. Now, the other thing that you might remember from the calculation that we previously did when we were looking at the correlation is the value of the R was 0.91 and the value of R squared was 0.83, and that was our 83% relationship. So you can see that the regression statistic is using the same information to calculate the same value, but the difference this time is it's actually going in a little bit more detail so that it's starting to look at the actual degree of significance of the relationship between these two sets of values. So if it's come down to the point where when you're doing your analysis of your data, you have looked at some sort of correlation, maybe you've calculated a correlation coefficient, and you think there is a causative relationship between your X and your Y values, then I would encourage you to just pop this into your paper, have a look at the regression analysis that you can easily calculate through Excel, and do exactly the same sorts of things that you've done before, which is to look for that p-value, look for that level of significance that you're interested in, compare the two, and in this case, as we've said, this value is less than our 0.05 value, and that means that I can have some confidence in rejecting my null hypothesis, that there's no relationship between these two variables, and instead I can conclude that there is some level of causative relationship between nasal length and nasal width in relation to kangaroos. We'll have just a little bit more of a look at some of the criteria that you might use when you're determining whether or not you can apply causation in our next video. Thanks for watching.